As the body ages, a silent and chronic inflammation gradually builds up across tissues, a phenomenon now widely referred to as inflammaging. This low-grade, systemic inflammation plays a central role in the development of age-related metabolic diseases, including obesity, insulin resistance, and cardiovascular dysfunction. Nowhere is this more evident than in adipose tissue, where aging promotes a shift from metabolically active fat to an inflamed, dysfunctional state. Nicotinamide mononucleotide (NMN), a precursor to NAD+, offers a potentially powerful strategy to interrupt this pathological process. One of the most promising mechanisms behind NMN's anti-inflammatory effects is its ability to restore and enhance autophagy, the cell's self-renewing and damage-clearing system. Through autophagy, NMN may not only suppress chronic inflammation but also reshape the metabolic landscape of aging adipose tissue. Adipose tissue is far more than a passive fat store. It is an active endocrine organ, producing hormones, cytokines, and signaling molecules that regulate systemic metabolism. In healthy, youthful fat, autophagy operates efficiently, ensuring that immune cells, adipocytes, and stromal cells maintain proper function and intracellular balance. But as aging progresses, autophagic activity declines, leading to the accumulation of damaged mitochondria, oxidative stress, and misfolded proteins within adipose cells. This dysfunction triggers immune activation, attracting macrophages and other pro-inflammatory cells that secrete cytokines like TNF-A, IL-6, and MCP-1. Over time, this chronic immune presence in fat depots contributes to insulin resistance, lipid overflow into organs like the liver and muscle, and systemic metabolic deterioration. NMN intervenes in this degenerative spiral by increasing NAD+ levels, which are essential for activating autophagy-related signaling pathways. Elevated NAD+ reactivates sirtuins, particularly SIRT1 and SIRT3, which play crucial roles in maintaining mitochondrial health, regulating oxidative stress, and modulating inflammation. SIRT1, for example, deacetylates and activates autophagy-initiating proteins, allowing for the removal of dysfunctional organelles that would otherwise act as sources of pro-inflammatory signals. At the same time, SIRT1 represses the activity of NF-B, a master regulator of inflammatory gene expression. In this way, NMN drives a dual approach, clearing inflammatory triggers from within cells while also silencing inflammatory gene transcription at its root. One particularly important process restored by NMN-induced autophagy is mitophagy, the selective degradation of damaged mitochondria. In aging adipose tissue, impaired mitophagy allows defective mitochondria to persist, producing excessive reactive oxygen species, ROS, and releasing mitochondrial DNA, both of which act as potent signals to the immune system. By promoting mitophagy, NMN not only reduces cellular stress, but also removes one of the primary sources of inflammation in aging fat tissue. This mechanism has been demonstrated in animal models where NMN supplementation resulted in decreased macrophage infiltration, reduced cytokine expression, and improved insulin sensitivity in adipose tissue, indicators of a reversal in the inflammatory phenotype of aging fat. NMN's impact on adipose tissue also extends to cellular composition. In healthy adipose depots, there is a balance between pro-inflammatory M1 macrophages and anti-inflammatory M2 macrophages. Aging tilts this balance toward the pro-inflammatory side. NMN, through enhanced NAD+ and autophagy pathways, may help restore the equilibrium, encouraging a shift back toward an M2 dominant profile that supports tissue remodeling, insulin sensitivity, and metabolic flexibility. This immunometabolic reprogramming may be one of the keys to reducing the burden of age-related adiposity and its associated diseases. Moreover, NMN doesn't act in isolation. It amplifies the body's existing metabolic control systems, making it an ideal companion to lifestyle interventions such as exercise, fasting, and anti-inflammatory diets, all of which also rely heavily on autophagic activation to exert their benefits. In synergy with these practices, NMN may offer a means to push aging physiology back toward a more youthful, responsive, and anti-inflammatory state. While large-scale human trials are still underway, early clinical data show promising reductions in inflammatory markers and improvements in insulin signaling in individuals taking NMN. Given its safety profile and its grounding in well-characterized molecular biology, NMN may soon become a central player in strategies aimed at combating metabolic inflammation and age-associated fat gain. In conclusion, NMN's role in reducing age-related adiposity and inflammation hinges on its ability to restore autophagic processes that deteriorate with time. By reactivating NAD+ dependent pathways and clearing damaged cellular components, NMN not only quells inflammation within adipose tissue, but also improves its metabolic functionality. This restoration of internal cellular housekeeping holds the potential to transform aging fat from a pro-inflammatory burden into a metabolically competent tissue, an outcome that could profoundly impact the trajectory of aging and chronic disease.